Hi, I'm Tom Wheat. I'm a principal scientist at Waters Corporation. I work in the separations laboratory testing new technologies for analytical instruments. One of the things we've been addressing lately is how to make the output of different detectors compatible in a UPLC analytical method. Our goal is to increase the amount of information that you can derive from a UPLC separation. Here we can demonstrate an approach to working with orthogonal detection modes, specifically the ACQUITY UPLC photodiode array detector, or PDA, along with the ACQUITY QDa mass detector. With this kind of information, we can confirm the identity of chromatographic peaks as well as examining them for impurities or inhomogeneities. We can also successfully analyze compounds that lack the chemical properties that create a particular detector response. And finally, we can use the orthogonal detectors during method development to track the chromatographic behavior of the sample components as we explore the separation space. The barrier that we have been encountering until now is a general limitation of all instruments. The detectors seldom have the same sensitivity and dynamic range. We are particularly interested in combining a mass detector with a PDA. For many analytes, the MS will be much more sensitive. When testing the dynamic range of the detectors, the ACQUITY QDa mass detector is linear with concentration and extends about 4 orders of magnitude. The UV response has a similar linearity in total range, but the linear response occurs at about a 100 times higher concentration. If we are to integrate the detectors within a single system, we must align the linear dynamic range of the detectors. The general solution is to divide the flow between the two detectors and to dilute the stream going to the more sensitive detector. Let's look at the schematic. Here, the flow from the column comes to a T. Most of the flow continues to the PDA, while a fraction crosses over to flow toward the MS detector. The fraction of the diverted flow is determined by the length and inner diameter of the crossover capillary. The flow to the MS is diluted with a makeup solvent. To help you accomplish the split and dilute technique, we have developed an ACQUITY isocratic solvent manager. It includes a set of restrictor module that can deliver different proportions of dilution of the column eluate. Each restrictor has a different crossover restrictor to give different levels of dilution. The tubing in each part of the flow path is controlled to give the controlled division of flow, and the T's and junction are carefully engineered to minimize dispersion. With the use of the split and dilute modules, the linear dynamic range of the mass detector is now shifted to higher concentrations so that it more closely aligns with the PDA detector. Now that we have successfully aligned sensitivity between the MS and PDA, an additional option is available to optimize detection. Since the split and dilute approach requires a makeup liquid, we can choose a solvent that gives the optimal response in the target detector. Here we're focusing on the ACQUITY QDa MS detector. For example, we can use a constant aqueous organic mixture to eliminate gradient effects on ionization efficiency. Or we can use propanol to enhance ionization efficiency, especially in the negative mode, without deleterious effects on the chromatography and viscosity. Similarly, we can add TFA to the chromatographic mobile phase to improve peak shape and retention. We then eliminate the ionization suppressing effects of this acid by reducing its concentration with a splitter and displacing the TFA with propionic acid. In conclusion, we've demonstrated how the PDA detector and the ACQUITY QDa mass detector can be combined with a split and dilute approach. This extends your options in using UPLC separations improving peak identification and manipulating chromatographic behavior and method development. To learn more, please go to waters.com/QDA. I'm Tom Wheat for Waters Corporation. Thank you.